Once again, I welcome in the class of hydraulic engineering. So today I will discuss the what is rapidly varied flow, and then uh, what is definition of the rapidly varied flow, and then hydraulic jump, and then what is the application of the hydraulic jump and the various assumption in the rapidly varied flow, and then I will discuss the hydraulic jump in a horizontal rectangular channel, and in this topic I will discuss the relationship between the sequent depth, and then relationship between the sequent depth and the Froude number. So let us discuss about the rapidly varied flow. So rapidly varied flow is a sudden change of depth occur at a particular stretch of a channel, and the change from one depth to another takes place in a very short length. Hydraulic jump is the best example of rapidly varied flow. What is hydraulic jump? So when a flow condition changes from supercritical to subcritical, the result is an abrupt rise of water surface by turbulent rollers is called as hydraulic jump or standing wave. The change in flow regime takes place over a relative short reach of a channel, so it is a local phenomena, and a hydraulic jump will form when water moving at a supercritical velocity in a relatively shallow stream strikes water having large depth and subcritical velocity. These are the various examples where hydraulic jump will form. Downstream of sluice gate on a mild slope, at the bottom of spillway, and when steep channel changes to horizontal channel. Let us discuss these are the various example of the hydraulic jump. Here we can see that this is the section 1, or the where the flow is supercritical, or we can say the Froude number is greater than unity, and this depth is called initial depth or pre-jump depth, and this depth is called post-jump depth. So after the jump, the depth is y2, and we can see that here the flow is subcritical. So when flow changes from supercritical to subcritical, then a formation of roller or hydraulic jump will form. This is the setup in a laboratory. Here we can see that the example of hydraulic jump. Here we can also say, we can see that this is the example of hydraulic jump. So what are the various application of hydraulic jump? So it is used to dissipate energy below the spillway, weir and sluice gates. It is used for mixing chemicals in water treatment plant and desalination of seawater. So this the application of the hydraulic jump, that is very much important for mixing chemicals in water treatment plant and desalination of seawater, to raise the water level on the downstream of a metering flume, and thus maintaining high water level in the channel for irrigation purpose. It increases weight on an apron and thus reducing uplift pressure under a masonry structure by raising the water depth on the apron. So due to the hydraulic jump, the weight of the apron will increase, and due to the increase in weight, the uplift pressure will reduce, and our structure will be hydraulic structure will be safe against the uplift. So this is the example of we can see that the this is the pre-jump initial depth, or it is also called sequent depth or conjugate depth. Y1 and Y2 is called sequent depth or conjugate depth. So what is sequent depth or conjugate depth? So the depth at which our specific force is constant is called sequent depth or conjugate depth. So before that I have discussed that what is the alternate depth. So the depth at which our specific energy is constant is called uh, alternate depth. So here we can see that this is the toe of the jump or start of the jump, and this is the end of the jump. And here we can see that this the y1 is called pre jump depth or sequent depth or conjugate depth, and this is the velocity head, and due to the roller or turbulent layer, the hydraulic jump will form, and this is the here the there is a end of the hydraulic jump, and we can say that this is the horizontal distance between the end of the jump and toe of the jump is called length of the jump. So sequent depth I have already discussed, or conjugate depth, that is y1 and y2, the two depth of hydraulic depth. with same specific force. And we have already discussed in the previous module that what is a specific force. So a specific force is the q square by ag plus az bar is equal to constant, and this expression is coming from momentum equation. Alternate depth is depth at which the specific energy is constant. Here we can see that Q is the discharge, A is the area of the channel, and Z bar is the distance of the centroid, distance of the centroidal distance from the top level, from the top width. So here we can return for at two section we can write the specific force, that is q square by a1g plus a1z1 bar is equal to q square by a2g plus a2z2 bar. So for this rectangular channel, what is z1 bar? So z1 bar is the y by 2. Here we can also say that z1 bar is y by 3. So these are the various assumptions. The portion of the hydraulic jump is considered as the control volume, and it is assumed that the before and after the jump formation, the flow is uniform and pressure distribution is hydrostatic. Similarly, the second assumption, the length of the jump is small such that losses due to friction on the channel floor are small, and the channel bed is horizontal. So I am going to derive the relationship hydraulic jump in a horizontal rectangular channel. So the first derivation, that is relation between sequent depth, or it is also called conjugate depth. Let us assume this is our hydraulic jump. This is this depth is called initial depth, and this is called final depth or post jump depth. Here we can see that the initial hydraulic jump will form. So we can write, let us assume a rectangular channel having the width is b and normal depth of flow is y. So we can write, let us assume y1 and y2. Let y1 and y2 be the pre-jump and post-jump depth. So we can write the, or it is also called the sequent depth. And so at sequent depth, the specific force at two section. So a specific force at section 1 is equal to specific force at section 2. Let us assume this is 1, this is 1, and at the end of the jump this is 2. So we can write a specific force at 1 is q square by a1g plus a1z1 bar is equal to q square by a2g plus a2 into z2 bar, or we can write q square divided by a1 can be written as b1 into y1 into g plus b1 into y1 into z1 bar. So for rectangular channel, z1 bar is y1 by 2. So it will be y1 by 2 is equal to q square divided by b into y2 into g, so plus b into y2 into y2 by 2. This is not, because width is constant, so this value is b and this is also b. We can write q square by b square into b divided by y1 into g plus b into y1 square by 2 is equal to, similarly we can write q square by b square into b by y2g plus b into y2 square by 2. So q square by b square is small q, we can write discharge per unit width. So let small q be the discharge per unit width. So we can write q square by b square is small q square. So small q square divided by q square by gy1 into b plus b into y1 square by 2 is equal to, we can write q square by gy2 into b plus b into y2 square by 2. B cancel, so we can write q square by gy1 minus q square by gy2 is equal to y2 square by 2 minus y1 square by 2. If I take common q square by g, so it will be 1 by y1 minus 1 by y2. So y2 minus y1 divided by y1 y2 is equal to 1 by 2 y2 square minus y1 square. So y2 plus y1 into y2 minus y1. So y2 minus y1, y2 minus y1, it will be cancel. So q square by g is equal to y1 y2 into y1 plus y2 by 2. So this is the relation between the sequent depth or conjugate depth. y1 y2 into y1 plus y2 by 2 is equal to q square by g. Second relation, that is the relationship between the conjugate depth and the Froude number. So let f1 and f2 be the Froude number at the beginning of the jump and at the end of the jump respectively. So for a rectangular channel, Froude number can be written as v by square root of gy, or if I write in terms of discharge, so it will be q by a square root of gy, or we can write q by area can be written as b into y square root of gy, or we can write capital Q by b is small q divided by g into yq. So here Froude number 1 can be written as q by square root of gy1q, or here it is also written as f1 square is equal to q square by gy1q. Similarly f2 can be written as q by square root of g into y2q, or we can write f2 square is equal to q square by g into y2q. So we can write here, we have derived the relation between the conjugate depth y1 into y2 into y1 plus y2 by 2 is equal to q square by g by dividing y1 cube on both sides. So we can write y1 y2 into y1 plus y2 by 2 is equal to q square by g into y1 cube, or we can write here it's also y1 cube. So y1 y1 cancel, so it will be y2 into y1 plus y2 divided by y1 square is equal to, we can write 2q square by gy1 cube, and q square by gy1 cube I have written q square by gy1 cube is f1 square. So here we can write y1 y2 divided by y1 square plus y2 square divided by y1 square is equal to twice f1 square, or we can write y2 by y1 whole square plus y2 by y1 minus twice f1 square is equal to 0. So this is the quadratic equation in y2 by y1. So we can write y2 by y1 is equal to minus b, so it will be minus 1 plus minus square root of b square minus 4ac, so it will be 1 plus 8 f1 square divided by 2a, so it will be 2. So y2 by y1 is equal to 1 by 2 into minus 1 plus minus 1 plus 8 f1 square. Negative value cannot be acceptable because this is the ratio and negative value cannot be acceptable. So negative value is not acceptable. So we can write y2 by y1 is equal to 1 by 2 minus 1 plus 8 f1 square. So this is the relation between the conjugate depth and initial Froude number or Froude number at the beginning of the jump. Similarly we can write y1 by y2 is equal to 1 by 2 minus 1 plus 8 f2 square. So we can also get this equation from here. If I divide by dividing y2q on both sides, then we will get the relation of this y1 by y2 is equal to 1 by 2 minus 1 plus 8 f2 square. So let us take the problem. The sequent depth ratio of hydraulic jump in a rectangular channel is 10.3. Sequent depth ratio means y2 by y1 is equal to 10.3. So what will be the Froude number at the beginning of the jump? So what is the Froude number? So we have the relation y2 by y1 is equal to 1 by 2 into minus 1 plus square root of 1 plus 8 f1 square, and y2 by y1 is given, that is 10.3. So it will be 10.3 is equal to 1 by 2 into minus 1 plus square root of 1 plus 8 f1 square. So it will be 1 plus 8 f1 square root is equal to 20.6 plus 1. So it will be 21.6. Squaring square on both sides, so it will be 1 plus 8 f1 square 1 plus 8 f1 square is equal to 21.6 whole square, so it will be 466.56. So f1 is equal to 465.56 divided by 8 square root. So it will be f1 is equal to square root of 465.56 divided by 8. So it will be 7.63. 7.63. So it will be B option is correct. Let us take the another problem. This question is asked in GATE 2016. The pre-jump Froude number for a particular flow in a rectangular channel is 10. So F1 is given, that is 10. The ratio of sequent depth, that is the post-jump depth to pre-jump depth. So let Y2 be the post-jump depth, and Y1 be the pre-jump depth. So we have to find the ratio. So this question is very similar to the first one. So it will be, we can write y2 by y1 is equal to 1 by 2 minus 1 plus square root of 1 plus 8 f1 square. So it will be 1 by 2 minus 1 plus square root of 1 plus 8 into initial Froude number is given, that is 10. So it will be 10 square. So 100. So value will be 0.5 into minus 1 plus square root of 801. So it will be 13.65. 13.65. So the ratio will be 13.65. So y2 by y1 is equal to 13.65. Let us take the another problem. The discharge from a spillway on a horizontal floor is 8 meter cube per second per meter width. A small q is given, that is 8 meter cube per second per meter width. If the depth before the jump, so let us assume depth before the jump is 50 centimeter. So depth after the jump will be. So we have the relation y1 y2 into y1 plus y2 by 2 is equal to q square by g. y1 is given 50 centimeter. So 0.5 into y2 into y1 plus y2. So it will be y1 is 0.5 plus y2 by 2 is equal to small q is given, that is 8. So 64 by 9.81. So we can write 0.5 y2 plus y2 square is equal to 64 into 2 divided by 9.81 into 0.5. So it is 26.095. 26.095. So we can write y2 square plus 0.5 y2 minus 26.095 is equal to 0. So we can compute, that is y2 is equal to square plus 0.5 x minus 26.095 is equal to 0. So it is y2 is equal to 4.86 . meter. So let us take the another problem. The conjugate depths for a hydraulic jump in a rectangular channel are 0.5 meter and 2 meter respectively. So the conjugate depth is given. Let us assume y1 be the depth before the hydraulic jump, that is 0.5 meter, and y2 be the post jump depth, that is 2 meter. Calculate the discharge per meter width. So in first part we have to find the small q. So we have the relation in case of rectangular channel, y1 y2 into y1 plus y2 by 2 is equal to q square by g. So we can, from here we can compute y1 into y2, 2 into 0.5 into 2 plus 0.5. So it is 2.5 divided by 2 is equal to q square by 9.81. So 2 into 0.5, it is 1. So 2.5 divided by 2, 2.5 into 9.81 divided by 2 is equal to q square. So q is equal to square root of 2.5 into 9.81 divided by 2. So it will be 2.5 into 9.81 divided by 2. So it will be 3.5. So small q is equal to 3.5 meter cube per second per meter width. In second part, we have to find what is the depth for which critical flow occurs. So we have to find the depth at which critical flow occurs. So depth at which critical flow occurs is called critical depth YC. And in case of rectangular channel, critical depth can be computed as YC is equal to Q square by G to the power 1 by 3. We have already computed the value of small q, that is 3.5 meter cube per second per meter. So 3.5 meter square divided by 9.81 to the power 1 by 3. So it will be, critical depth will be 3.5 whole square divided by 9.81 to the power 1 divided by 3. So it is 1.08 meter. 1.08 meters. So this is the critical depth.